Y'all hearing me okay? Sierra and Courtney. All right. I'm going to get started on this, and then we should be able to finish this tonight. But chapter 10 is about the concept of probability, and it's rather long if you don't break it up into two parts. So what we'll do is just talk about basic probability, and then two methods for counting very large numbers of things. And by doing that, then when we come back after the midterm, which, this time next week, then we'll have, we can take a little bit of leisurely pace, and it won't be so arduous of a road. All right, so 10.1 and all of chapter 10 is based upon probability, or about different aspects of probability, but this 10.1 is basic probability. First thing we want is just a few definitions. An experiment is a controlled operation that yields a set of results, like tossing a coin, rolling a die, rolling two die, doing anything where you're unsure of the outcome. And oftentimes in probability, things like this, like gambling type things, are commonly used because those are things where we don't know the outcome. But there are many different things that can be done as well, because probability is what's used to set insurance rates. It's what's used to set any number of rates when you're talking about ventures that maybe a company is going to take, and you have to break it down into probability, and we'll see those later on. But for the most part, very simple ones can be illustrated by some kind of a game. Now, a sample space of an experiment is all the possible outcomes. Like for a head, there's only two sides on that coin. There's a head and a tails. For the six-sided die, there's 1, 2, 3, 4, 5, 6. 6 different outcomes. Now, an event is going to be some sub-collection from that sample space that we can hone in on and work on finding some information about. So like if we wanted to say the event of rolling an odd number on a single die, well, 1, 3, and 5 are are odd numbers. All right, so what's going to happen is we're going to find the probability of certain events happening based upon how many of those events exist, and then how many values are in the sample space. Now, some books, well, often, most books, I find, they make probability formulas more complicated than they need be. They'll talk about theoretical probability, which is something like rolling a die, or tossing a die, or tossing or flipping a coin. But in reality, it works the same way for empirical probability, which is where we go out and collect things we've never seen before. Like if we wanted to go to everyone in Delgado and find their eye color, we'd physically have to do that and go out and write that information down. And that would be what's called an empirical experiment, empirical probability, because it's just based upon something where the information has to be taken down, as opposed to something like a die or a coin, or even with cards. We know how many there are certain things inside of there. But basically, we calculate probability like this. The probability of an event A, we'll call it, and that could just be anything for right here, is the count of all outcomes in A divided by the count of all possible outcomes. Or another way to look at it is the number in your sample space. So let's look at this one. Probability of an odd number, and this is on a die. All right. Well, we already saw there's 3 odd numbers. Oops. What did I do? There's 3 odd numbers. And then out of that die, there's 6 total. And then if we simplify that down, which is usually one that you want to do with probability, you never leave a fraction in an unsimplified form. Sometimes you can write it as a decimal. But the probability of rolling that odd number on a die is 1/2. Based upon 3 odd numbers, and then the total number of values on that die, which is the denominator. Now, the probability, we'll come back to that right there. The law of large numbers. I'll explain that in a bit. But the probabilities always have to lie between 0 and 1. The smallest a probability can be is 0. And when we say probability of 0, that means that the event will not occur or cannot occur. And if it's 1 on the opposite side, that means that it's certain to occur or will occur. And things in the middle are, well, 0.5 right here, that's 1/2. This would be like 1/4, and this would be 3/4. So what's always going to happen with probabilities is the probabilities will never be less than 0 and never be greater than 1. If you ever calculate a probability and have one of those two situations, less than 0 means it's going to be negative. So you can never have a negative probability, and you can never have a number that's a probability that's greater than 1. Now, the law of large numbers is something that relates to how we find out things about certain experiment, by certain experimentation. Let's see if I can find something and show you. There was a coin flipper on here and they changed it. So let me just kind of show you this for explanation purposes. This is a little coin flipper, and people can go here if they want to say flip a coin 10 times, they can do it, or 5 times, or however many times you want to do it. But what this shows you is it keeps track of everybody that comes on and flips a coin. Now, theoretically, you would expect that that's the way we calculate the probability of a coin flip. Like there's one head over 2 sides of the coin, there's one tail over 2 sides of the coin. So the probability of a head is 1/2, and the probability of its tail is 1/2. So you would expect that when you flip a coin, you're going to get either a head or a tail. There's 50% chance of getting a head, 50% chance of getting a tail. But if you notice here, however many times these been flipped, and this is 972,998, and this is 972,665. So probably about a little bit less than, well, they show us. It's 1,945,663 flips total. And these are not perfect, all right? But what the law of large number tells us is the more times we do something, something like this will start to conform to what we would expect it to be. So we would expect to get about half and half. And that actually right there, those numbers are probably about, pretty close. Probably the more times you get to do it, and more times you do it, the closer they're going to come to being even. If you're interested in that, there's a little video here that explains that concept. But this right here also explains the concept of population of girls. All right. And it just shows that over time, that as the number of births increases, well, you would expect it to be half girls and half boys usually. But that doesn't happen in reality. It started out at 0.4 or 4 out of 10 girls. Then it went down to 3 out of 10. Then it got higher. Then it got over 5, went up to 0.6, and then finally starts coming back down again. So as the number of births increase, it starts closer to hugging that line. And that's essentially what the law of large numbers is. If you want to see that little video to help you learn a little bit more about it, if you kind of want to see it, it's not a major concept. It's just that other than the fact that that's how probabilities are essentially determined. Theoretical probabilities come from this experiments happening over and over and over, or at least that those theoretical results end up matching. Now, if you have a sum of probabilities, in other words, if you notice that the probability of a head is 1/2, the probability of a tail is 1/2, 1/2 and 1/2 adds up to 1. If you think about the die, we had 3/6, and if we also brought into the even numbers, that would be 3, 6, 3, and 3 add up to 6/6, which is also 1. So the probabilities of all possible outcomes of a given experiment have to add up to 1. And essentially where that comes from is this thing called the complement rule. And you saw a little bit about that when we dealt with it in chapter 2. But the complement is just what's not in the event A, or the what do we call it over there? We weren't talking about events. We're talking about sets. So what's in a set and what's not in a set A have to add up and equal to 1. And that's where this complement rule comes from. So keep that in mind. It's going to be used inside of things here. Let's fiddle around with this before we leave here. This is some information that's come from people that have donated blood, like 500 people. All right, so the probability of AB is equal to 16 over 500. And I can take that and whittle that down to a fraction. I'm sorry, decimal. .32. All right, now what about the probability of O blood? Well, it's 210 over 500. All right, now let's say that I ask, what does that say? Okay, can you see that little chart? So this was just a little chart that showed during a blood drive the number of out of 500 people that donated blood, what their blood type was. So the probability of AB is 16 over the total of 500. Does that make sense, Latrice? All right. So the probability of O was 210 over 500. So that's 0.42. But let's say I want to find of not AB. Well, there's two different ways I could do it. I could either take all the ones that's not AB and add them up, and that would work, and then divide by 500. Or I can take 16 and divide and subtract it from 500. And so there's 484 of those. You would get it the same way if you took 223 plus 51 plus, and so that's 484. So that's kind of using the complement rule. Formal complement rule would be like this. All right. It's just going to look messier, so that's why I didn't do it. 1 minus the probability of AB. Keep hitting the wrong thing. So that's really all there is to probabilities. This right here is what we would call empirical probability because it's based upon things that are observed. There's no way you could know this if because it was data that was collected. So therefore, you got to have some kind of information given to you, unlike the coin or a deck of cards or a die, where you kind of know what's on there. So that's really what basic probability is about. So we want to take basic probability into account here, and then we're going to talk about these two counting methods. The first one is called, sometimes called the fundamental counting principle. And I think a lot of people know about this intuitively, but it really, every time I see anybody try to explain it and the definition, it ends up being kind of convoluted to me. But look at this. So if one experiment can be done in M ways, and a second experiment can be done in N distinct ways, then by combining the two experiments, they can be done in M times N ways. Let me show you what this means. Let's say you got a couch, and there's two choices in the material. There's leather and there's micro suede. And out of those two materials, you can have either tan, white, red, or green. And that applies to both. Well, look at all the possible options. There's 2 times 4, which is equal to 8 distinct ways to order the couch. So there's leather, tan, or white leather, red leather, green leather, tan microsuede, white microsuede, red microsuede, green microsuede. And the reason why the fundamental counting principle is important is because most of the time we don't care what those values are, and we don't necessarily need to see a little tree like this. We just need to know how many of them there are. All right, so look at this again. Let's say now we add a third choice to that sofa, where you can have a built-in recliner or not. So at the bottom of each one of these, we've got 2 little forks coming off. Yes and no. Yes means a recliner. No means no recliner. So notice what that does. Now you got leather, tan, with a recliner, leather, tan without a recliner, leather, white with a recliner, leather, white with no recliner, leather, red with a recliner, yellow, red, leather, red with no recliner, green leather with a recliner, green leather with no recliner. And then the same thing over here. Now, see, there's 8 just on that side alone. So what does that look like mathematically? That's 2 times 4 times 2, which is equal to 16. So there's 16 different types of sofas that come out of there. Each one of them would be unique. So that's the first thing, the counting principle. It can also be used with things like license plates. Believe it or not, license plates are determined by combinations, in Louisiana at least, of 3 letters and 3 numbers. So I'm assuming here, unless you tell me different, that everybody knows how many letters are in the alphabet. There's 26, right? So that means for this first letter, there's 26 choices. Second letter, 26 choices. Third letter, 26 choices. And then the numbers each give you 10 choices because you got from 0 to 9 as your choices, which is 10. So 10, 10, and 10. Now, if you wanted to find out how many license plates there are, let's just call it a scheme, I guess. Well, it's 26 times 26 times 26 times 10 times 10. And I think that's, I know the number because I've done this a number of times, but it's 26 times 26 is, so that's 17576, and then you got 3 zeros. That's what these 10s do. They add an extra 0. Oop. So the number of license plates that can be created with this system that we have in Louisiana is 17,576,000 unique ones. I'm probably sure there's some that they don't use. Maybe that they have something that they might be deemed offensive. And then maybe there's other ones that they keep for local, use, like for government use or what. But that's more than enough for everybody in Louisiana to even have a car, because I think there's only like 7 million people. All right. So that's the counting principle. All right. Now, permutation is closely related to the idea of the counting principle. It's just that with a permutation, it's ordered and you don't use anything more than once. The most common type permutation is this thing, and you might have seen this on your calculator. But that little thing, n factorial, most scientific calculators have it, and probably most calculators nowadays have that on there. All that is simply means is whatever number you put in there and then hit that little key, that it's going to keep going down the line, subtracting one and multiplying. So 7 factorial would be equal to 7 times 6, 5. So that's a form of accounting principle. It's just that it's called a permutation because um, it's orderly arrangement because nothing is used more than once. This would also be useful, like if you were told um, on license plates that you can't have any repetitions. Then it would be 26 times 25 times 24. And then over here it would be 10 times 9 times 8. If you were told no repetitions. All right, now this formula right here, the number of permutations when selecting R objects from N objects, it's got kind of an awkward title or name, but that's essentially what it is. And order is important. That's the reason why it's permutations. It's written like this. And what this essentially says is if you have a big bag of items, like you could say, anything like a bag of pool balls, and there's what is it, 15 pool balls, and you go in there and you pull out a handful. Well, how many different ways is there to do that? And that's essentially what this is doing, and it's very helpful for um, doing certain types of things. So let's look at this. I may have to write this on the board. See if I can do. So what the 17 is, the N, remember, is always your larger number, and the R is a number that's going to be smaller. If it's the same size, it can technically be the same size as N, but then there's only going to be one way to do that. But you're always getting a smaller group out of a larger group. So let me just write this on here. All right, and as I said, the formula was and the numerator is n factorial, and down here is the difference between the two, n minus r factorial. It's always n minus r because you don't want to have negative number down there. Okay. So I'm just going to follow this pattern. So that ends up being 17 factorial over 13 factorial. All right. So that's 17 minus 4. Now, the calculator that's built into Alex will have that. In some cases, it may not. The thing about the Alex calculator, it's not always there. I don't understand how they determine. when to put it there. So I don't have an emulator for that one, but I'm just going to so I'm going to show you by hand. And if you can figure out with the calculator, then go ahead and do it. And the way to do that would be to put in whatever calculator you got into Google, type it, and then put permutations. And then you'll get some kind of instructions about it. All right, so I'm just going to show you how to do it by hand. So what I'm going to do, I'm going to count down until I get to 13. Remember, these are being multiplied, and they're being multiplied all the way down to 1. All right? So rather than go all the way down to 1, I just left this 13 so that we could notice that these two things are on top of one another in a fraction. So that's 1. So all that's left is 17 times 16 times 14. And that's a lot easier to do than type, because if you put 17 factorial in a calculator, you're going to get a huge number. You either have to use the permutation formula in the calculator, or you got to do it like this. So this comes out to 57,120. So to go back over to that example, out of the 17 contacts in their cell phone, how many ways can Shanna set the first 4 speed dial contacts? Well, that's what we just showed. 57,000. Sorry, 5,020. I forgot what it was now. Did I leave something out? So 1 right there. So 57,120 different ways. All right, here's another one. A DJ has a choice of 7 songs in the queue. He has to pick 3 different songs to play in a certain order after the commercial break. And its order is important, so that's how we know this is a permutation. So he's got a choice of 7, but he can only do 3. So let's do that over here. So the big number goes on top with a factorial sign, and then this is the difference between the two, factorial. All right, and said, is these numbers are getting smaller, so you might be able to put 7 factorial in the calculator and then do 4 factorial, but and divide. But I'm just going to do it this way because I think this is quicker. So 7 times 6, 5. So there's 210 different ways. Thank you, Sarah. Yeah, to do it. That's where order is important, okay? Order is important. There's one other kind of digression before we go to the combinations, but if you've got duplicates, and I'm trying to remember what those things and some of the ones that they do in Alex are kind of silly to me, but if you've got something that has repeated objects in it, like for example, the word Mississippi has repeated I's, it has repeated S's, and it has repeated P's. Alabama has repeated A's in it. All right. So obviously, you can't really, since you're dealing with things that are identical, duplicates, like A's, it doesn't matter, what where one A is or the other. If you got A at the beginning and the A in the third place, they're both the same thing. So that's going to change how many different permutations there are. So this formula just makes it look a little bit more difficult than it is. But essentially, what you're going to do is you divide out. Well, first of all, your numerator is still how many letters are in the word, factorial. And then you divide out how many repetitions there are. So let me put this over here. All right, first of all, Alabama's got 1, 2, 3, 4, 5, 6, 7 letters in it. Am I correct on that? All right. So in the numerator is going to be a 7 factorial. Now, the formula makes it look like it kind of complicated, and that's why I wanted to go over this one first. This one's only got one word that repeats. All right, so what we're going to do is we're going to put it down there, the one that number of times it repeats, with a factorial sign. And the ones I think in Alex, what they do something kind of silly. They'll have give you 3 things that repeat, but one of them doesn't ever repeats. Like if they mention, B, you would just it would be putting a 1 factorial down there, which doesn't really do anything. So let's look at it for Alabama, and then we'll look at it for Mississippi and see how it changes. So that's 42 times 5. That's 210. So because we have 4A's in there, then that's going to cut down on the number of distinct passwords that would be, because one A is as good as another A. Right. Let's do the same thing. All right, so if I'm not mistaken, there's 11 words, right? I mean, 11 letters. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. Uh, P is twice. All right, so that means in the numerator we get 11 factorial. But now, as this formula shows you, you see that they got P factorial, Q factorial, R factorial, repeating on down. Well, that just means that you can have as many repetitions as need be, the dot, dot, dot. But these are multiplying one another. So and then when you get more than one down there, it's a little bit more complicated, but not too bad. So let's look at it. I'm going to go down to 1. I'm sorry, to 4. And I got 2 factorial, so it doesn't matter which one I take out. So I'm just going to take out that first one. And then see if I can make this a little bit neater. Let me leave the line too long, but that's no big deal. Now, 4 factorial, I'm going to write it over here. So then I'm going to write that down there. Now, the 2 factorial is really just 2 times 1. So now all of this that's left over is written down there. And what I can do now is just divide those out any way that see fits. Now, since we're talking about the number of ways for something to happen, you're never going to be left with fraction. You should lose all of the pieces down in the denominator. So the way I'm going to do it is 3 times 2 is 6. And 2 times 4 is 8. So then what I got left up there is 11. Times 10 times 9 times 7 times 5, because the 8 and the 6 are gone. So down here at the bottom, the only thing is left is a nice fat 1. So what does that come out to? We just multiply it out. So 11 times 10 times 9 times 7 times 5. So there's 34,650 different ways to arrange those things. Or you could think of it in the way we did for Alabama about distinct passwords. All right. So the last little bit then deals with something now called a combination. Now, a combination is different only in the sense that we're not worried about order of things. And people might wonder what this is all about. Well, if you look at the term combination, you have a thing called a combination lock, and you have to enter numbers in a distinct order in order to open it. That's really a misnomer. If we were going to call it something, it would be a permutation lock. But what a combination is, and something that most people know about, is the lottery numbers. Because as the lottery numbers are picked, they don't have to be held in that order. They just have to you just have to have those same five numbers that you picked in any order. So in some ways, combinations is a lot more useful for probability. But notice that what's different here is it's exactly the same, except that in the denominator, there's an extra r factorial now they're multiplying. And what that r factorial does is it essentially divides some of them out so you don't end up with so many. All right? So let's look at this. Let's do this one first. Then we'll do probably just do this one. I need to do all three of this. Okay. A committee of four teachers is to be chosen from a faculty of 25. How many committees are possible? All right. So first of all, let me go ahead and write it over here. Big number is always over there on the left. Comes first. All right. So now, well, I should have put the formula for you over here. And so I kind of probably should have left a little extra room. All right, so the 4 factorial comes first. And then here is 25 minus 4 factorial. Okay, so it's still the difference down there in the denominator, just like for the permutations, but we got this extra one here. So once I go ahead and do the subtraction, this is going to be 21 factorial. And the good thing about, the good thing about these is that 21 is going to take out an awful lot of the numbers up there, because 25 times 24 terrible fraction, but we'll deal with it for right now. And then this is the 4 factorial. We'll take care of that later. Now, those are going out. So what we're left with is, probably just try to type it out here. Let's see, that'd probably be And then the 4 factorial is 4 times 3 is 2 times 1. We don't really need to write the right one if we want to, but I just want you to see that it's still there. Because once we get everything but the 1 there, then that's what the whole number is. So now, take them out as best as we can. 2 goes into there 11 times. 3 goes into 24. You could also look at this as 12. 4 times 3 is 12. And 12 goes into 24 twice. That's probably the easier way. And so what we're left with is 25 times 2 times 23 times 11. So 12,650. Well, look. Oh, you're right. You're right. Thanks. 12 goes into 24. No, 2 times, doesn't it? 2 times 12 is 24, right? 4 times 3 is 12. 12 goes into 24 twice. Well, but it wouldn't matter how you did it, because if 3 goes into 24 8 times, 4 goes into 8 twice. However you do it, just as long as you divide them all out, there's always, almost always more than one way to do it. All right, so let's look at that last one. Calculate the lottery, a number of lottery selections, selecting 5 numbers from 1 through 46. And then I'll leave this one for another time. But the reason why I had 2 of them was I just wanted to show people that what you'll notice with the lottery is if they raise up the number of numbers to pick from, it's going to make the number of selections larger. All right. So pick 5 out of 46. and this is 41. All right, so $41. All right, so I stopped up there at this one so I could take those out. And so what I have left is 'yeah. Like I said, you can take them out anyway, but let's just. I'll take them out. What you suggest? 5 goes into 45 9 times, right? So 4 is going. Now, um, 44 is divisible by 4, and that's 11. So 4 times 11 is 44. 42 divided by 3 is 14. And the only thing I left is the 2. I can take it out of any one that's even. So I'm going to take it out of this one just so it won't be so big. So 2 goes into 46 23 times. So now the numbers are a lot less big, I guess you could say. Less intimidating. But as I had said, yes, there is a way, um, like that official calculator, that TI2X thing, it's got them on there. I just always have to Google it every time I want to figure it out. All right, let me just see something. Let me just see if there's one on here somehow. I think I might have found one at the TI site. It's coming up, and I'll be able to show it to you. Because you can do it real quick on there if you want. And they do have it also, like I said, in Alex, but I don't know that it's always there. Sometimes they take that, they don't have the calculator. So it's probability, click, hold on. No, I'll show you. It is installed now, and I'll show you Wednesday. Because Wednesday will be a review of anything throughout the whole semester. So bring any questions you got. And like I said, is but this ends up being 13,707,000. No, I see. It's 1,013,000. 1,370,754. So it's going to take a while, but I'll remind me if I want. Well, we did. We took 5 into 45 was 9. What were you talking about? Jamel, what were you talking about? You're talking about over here? Talking about right here? If you had wanted to bring this all the way down to 5 factorial, then you could take out that 5 factorial at the top. But 5 factorial, we don't know if it's going to divide into 41 factorial. Which the reason why I did it like this, where I stop at my largest number down here, is because these are factorials. But one thing I do know, if I have one thing, no matter how big it is, divided by another thing, then these become 1. So I could have started with a 5 factorial if I'd wanted to, but it's going to probably be a lot more work like that. Then you'd have to write out the whole 41 factorial instead of just the 5 factorial.